Hello everyone. Here's an example from section 2.6 where you are building mathematical models, building functions and using them to solve applied problems. And number 25, section 2.6 number 25 is called constructing an open box. It says an open box with a square base is to be made from a square piece of cardboard 24 inches on a side by cutting out a square from each corner and turning up the sides. So you see the figure shows you start with a square of cardboard, you cut out squares from the corner, an unknown dimension of x on a side, you throw that away and then you fold up the edges to make an open box. We're supposed to express the volume of the box as a function of the length of the side of the square cut from each corner. There's the hard work. And then we're supposed to answer what's the volume of when a 3-inch square is cut out, what's the volume when a 10-inch square is cut out, and finally graph that volume function and say for what value of x v is largest. So we're really trying to design this box so that we get an open box of the largest possible volume. Okay, let me move this over here, maybe under my talking head, and bring up my my work for this problem. So first of all, that picture of an open box, you understand, looking at this from the side, we should be able to see into the top of the box. And then I think that maybe the hardest work of the problem to get it launched right is to be able to express the dimensions of the box all in terms of x. You know, the volume, we're supposed to do a volume function. The volume of a rectangular solid is v equals the product of the dimensions, right? Length times width times height. But I don't want a function that's got 3 different variables in it. So it's necessary, if I want to make, as they ask, I want to express the volume of the box as a function of the length x of the side of the square we're cutting out from each side. We need this all in terms of x. So this dimension is going to be x. When you cut out a square of dimension x and fold it up, the height of the box will be x. But you have to think a little bit. When you start with a 24-inch square and you cut x out of one corner and x out of the other corner, you're left with a dimension of 24 minus 2 times x. And of course that's going to be the dimension front to back as well, because we started with a square. Okay, so with that in mind, volume in terms of x is going to be the product of these 3 dimensions, 24 minus 2x times 24 minus 2x times x. And then I've got to do a little bit of algebra to clean this up. I'll do a FOIL product here and get 24 times 24 is 576 minus 96x squared plus 4x squared. And then I'll multiply through by x and put things in descending powers of the variable to get this cubic polynomial, 4x cubed minus 96x squared plus 576x. And that's a nice clean answer to part A. Right, the volume, a function for the volume of the box as a function of just the variable, the length of the square that's cut out of the side. Then part B and C are on the easy side, really, because they just say what's the volume when you cut out 3 inches from each corner or cut out a 10-inch square from each corner. And this is essentially just figure out v of 3 and v of 10. You can do that just by plugging those numbers in here and cranking them through. I'll confirm that in a minute, but I get 972 cubic feet and 160 cubic feet. Notice the units on here had better be feet times feet times feet. The dimensions are all in feet. Oops, they're all in inches. Wonder if I can get in here and edit this while I'm at it. Inch, inch. There we go. As I was saying, they should be cubic inches, right? Inches times inches times inches for a volume. All right, then proceeding down here, I'm supposed to graph this on my calculator. All right, so I'm going to my calculator, and you can probably see what I have on my Y screen here. 4x cubed minus 96x squared plus 576x. And when I graph that, I have to mess around with the window a little bit to get a picture like this that looks like a complete graph. You sort of see that? I had to get a window that had a height of about 1200 on the y-axis, and my x's go from 0 to 13 or so, and I get this part of the graph. If I think about it, there's more graph that happens outside of this window, but when you think about it, the natural domain of this problem is not all real numbers, because you're cutting this dimension. I think you can see this dimension, x, and that full dimension of the cardboard you start with is 24 inches. So if you think about what x could be, it's got to be at least 0, and it really can't be any bigger than 12, I guess. If you cut out corners of 12 inches on a side, you're cutting the whole box away. So really the natural dimension of this, or rather domain of this problem, in this problem situation, that's a better look, is from 0 to 12. X has to range from 0 to 12, which is basically where it's positive there in the first part, on the first part of the graph in the first quadrant. Okay? And you can also kind of see what's going to happen with maximizing the volume. The maximal volume is going to happen at that local max of the graph, and I'm just going to locate that with second calc max. Let me, while I'm at it, confirm my earlier solutions. If I press trace and then hit 3 enter, it's going to take me to where it's going to take the cursor to where x is equal to 3, and I hope I get an output there of 972 cubic inches. Good. And of course I could do this for 10 as well. But let me go ahead and do second calc maximum, enter, and then I need a right bound. I need to move my cursor to the left of the local maximum. I suppose you're glad to see that I'm getting a error there. Let's see. Second calc maximum. Left bound. Right bound, guess. Good deal. So I see that I got my maximum volume where x is equal to 3.99999. I'll bet that's exactly 4. I would round to 4 to many decimal places. It's happening at 4,1024. So I'm going to go back down here and say volume is maximal when x is equal to 4. I suppose in an answer here I might even want to say inches. Cut 4-inch squares out. And I believe that is what they're asking. For what value of x is v largest? So this is really the answer to part D. If I wanted to do more, I suppose I might say that according to my screen, that actual maximal volume of the box is 1,024 cubic inches, just by the way. Okay, have fun.